Okay, today we are looking at sets. These are going to be very useful mathematical constructions. Let's see what a set actually is. Okay, so a set is simply a collection of distinct elements. And let me show you how we can define a set here. I'm going to define the set F, okay? We like to use single letters to name sets. F is going to be for fruits. And I use a curly brace here, and then I just list the elements of this set. And we're going to have, in here, we're going to have apple, banana, coconut, and date, okay? And then we finish it off here with another curly brace. So this defines what elements are inside my set F, okay? So we can say that this here, that's going to be the name of my set. And then all of these things in here, these are all of the elements, right? That's what's inside of set F. So it's pretty straightforward. We can define many different kinds of sets in many different ways, but this is the basic construction. There's a couple of other important symbols we want to know. We're going to look at, let's say we have apple. Okay, so apple turns out is an element of the set F. And so what we have here is a new symbol that describes, this is the element symbol. So it says that apple is an element of F. What if something's not an element of this set? For example, oak. Okay, we say that oak is not an element of F. Very simple, right? So the idea here, this symbol represents when something is not an element. Okay, so that's just a basic introduction to how we can define a set. But what if we want to define a set that has more than 4 or 5 or 6 elements, where it becomes very tedious to write down every single element? In fact, maybe you have an infinite number of elements. Well, then we're going to want to use a better way to describe what's inside of a set. We're going to use set builder notation. All right, so let me first define a new set using the original method. I'm going to define the set A, and this is a set that consists of the elements 2, 3, 4, and 5. Okay, so there we go, a set of 4 elements. Now notice that there's a clear pattern here. This is sort of a set that consists of all of the integers from 2 to 5. So I can describe this set using set builder notation that basically encodes a pattern. And if you follow that pattern, you wind up with this set of 4 elements, right? So let's do that. You're also going to use a curly brace for set builder notation, but first we define a variable. In this case, we'll say this set consists of all x, such that x is an element of the set of integers, and 1 is less than x is less than 6, and then we'll close out the set here. Okay, so let's try and understand what we're writing down here. First, we define a variable, right? And then this bar, we can sort of read this as such that. And then here we have what we call a rule, or sometimes also known as a predicate. Same idea. Okay, so we've got a variable x such that x is an element of the integers and 1 is less than x is less than 6. And so if you follow this rule, you're going to take all of the integers so that are between 1 and 6, not inclusive. Well, that's going to be the integers 2, 3, 4, and 5, right? So there we go. And you can see now this is sort of like writing a little computer program to define what your set is. It's just a rule with some variable that you're going to be using to plug in or follow the rule, right? And very clearly, we can modify the rule to create very large sets. This one's only 4 elements, but imagine if we made this, a 16. Well, now you've got 10 more elements, right? You can make it 116 and have 100 more elements. You could even make infinitely large sets this way. Maybe you just have it so that it's x greater than 1, right? That would be an infinitely large set now. So set builder notation is very powerful. It allows you to define very clearly extremely large sets following this kind of rule. There's another way we can also use set builder notation. So this is one way, but this part here, when we're saying that x is an element of the set of integers, well, that's what we call a domain, right? And so we can use that domain instead of just a variable here. So let me define the same exact set right here. We can say that A is the set of all x that is an element of this set of integers such that 1 is less than x is less than 6. Okay, so in this case, what we're doing is we are adding in our domain here first, and then we're going to have our rule. So this is another valid use of the set builder notation. Okay, let's take a look at a next very important point here. We're going to look at the idea of an empty set. All right, so an empty set is an interesting concept. It's literally a set with no elements in it. And we can represent this either using the curly braces that we had before that are empty, there's nothing inside, or we can use this with sort of a symbol with a zero with a stroke through it. Okay, so both of these symbols represent the empty set. Okay, so for example, let's say I had the set P, and I'm going to define this set P as an empty set. Okay, so what does this mean? Well, it means that P is literally an empty set that contains no elements. Now, why is this important? Because this P is the empty set. This is not the same as 0. We cannot say that P is 0 because 0 is an integer, right? Or a real number. It is an element. So having P equal 0 is not the same as having an empty set. All right, so that's an important distinction. 0 is actually an element that you could put into a set. All right, so now let's take a look at some important uses and operations essentially that we can use with sets. So the first operation we're looking at is the union operation, and that is represented with this symbol here. It looks like a U, and you can say this is A union B, and that represents the set of all elements that are in A or that are in B. It's basically the combination of all the elements in set A plus all of the elements in set B, right? So that's what we're doing here. Let me illustrate this for you. So how about we define our set A here, and this is going to include, how about our apple and our banana. And then I'm also going to define our set B, and that's going to include, how about our coconut and our date. Okay, so here we have two different sets, and what we can do now is we can put them together, right? So we're going to have A union B. Now, what does this represent? Well, this is going to be a new set that contains apple, banana, coconut, and date. There you go. Okay, it's just the combination of all of the distinct elements that were in set A and all of the other elements that were in set B. Okay, now logically, this is similar to the logical OR operator. And so that's one way you might use this in the future. Let me show you another way we can use this. So how about we define two new sets here. Okay, so I'm going to define my first set here. How about the set C? That's going to equal the numbers 1, 2, 3. And then I will also define the set D, and that's going to equal the numbers, how about 3, 6, and 12. Okay, so there we go. 3 elements in each set, and now what we're going to do is we're going to have C union D, and we want to know what is this new set going to be. Well, you're going to have to combine all of these elements basically. So it'll be the numbers 1, 2, 3, 6, and 12. Okay, so this is C union D. Now notice, even though the number 3 is present in both of these sets, when you combine them, a set only includes distinct elements. So you can't have the number 3 represented twice, right? That element is only going to be in the set one time. Okay, so this is the union operator. Let's look at the next operator. Intersection. So here we see the new notation. It's an upside down U. Sometimes we call this a cap, right? So sort of like a cap. Sometimes we call the U a cup. Those are alternate notations, but this we can read as A intersection B. So this is going to result in a new set that is the intersection here. So it's the set of all elements that are in A and also in B. Okay, this is basically the logical AND operator. So let's look at an example here. Just as before, we're going to have our set C, and that was the elements 1, 2, 3. And then we also had our set D, and those consisted of the elements of 3, 6, and 12. Okay, so now we want to use the intersection operator. So we're going to have C intersection D, and this is going to give us a new set. Now, what do you think are going to be the elements in this set? Well, it's going to be all of the elements that are in C and also in B. So this element 1 is in C, but it's not also in D, so we can't include it. Same thing with the number 2. It's not also in D. The number 3 is in C and also in D. So we do include the element 3. And in fact, that's the only element because 6 and 12 are not also in C. So this intersection between C and D results in a set with only a single element, in this case, the number 3. What if we try this with two other sets? Okay, what if we try this with, how about the set E? Let's call this 1, 2, 3. And also, how about the set F? Okay, let's define this as the elements 4, 5, and 6. Okay, so now we want to do this again. Let's get the intersection. Oh, I guess we're intersecting E and F. Okay, so what is this going to be? Well, if you notice now there's no overlap. There are no elements that are shared in E and also in F. And so what we're going to get is an empty set, also known as the empty set here. Okay, so the intersection is basically the logical AND operator. Let me see if I can show you a graphical way to interpret these operations. So it's very common to illustrate these kinds of union operators using these kinds of Venn diagrams. We kind of see how things overlap or don't, and what the result is going to be. Okay, so first let's say that this circle represents set A, and this circle represents all of the elements in set B, and we're going to do A union B. We want to know what do we get as a result. So what we're going to get is we're going to look and get all of the elements here just like this. So it's all of the elements. So if an element is in set A or is in set B, then it will be in the new set A union B. And so that means you grab all of the elements that are present here. Let's take a look at the intersection now. Okay, so again, this is set A and this is set B. So we're going to have A intersection B. Let me draw that a little bit better. Intersection B. So what's going to be in this new set? Well, the elements in this new set must be in set A and also in set B. And so in this case, we are only going to grab this part where they overlap, because only in this central region do we have elements that are in set A and also in set B. And so that's how we can visualize the union and intersection operation. Okay, hopefully this was a good overview of sets, and we will be using this as a tool in the future.